Traditionally, the teaching of optics is based upon the fundamental laws of reflection and refraction. The behavior of lenses is treated as an outcome of these laws. In this film, we shall show an alternative approach which emphasizes the image-forming properties of a lens. But first, we see something of the property of light by casting a strong beam from this quartz iodine lamp onto a white sheet of paper. It is evidently straight, and it may be reflected using this mirror. Light may be bent by passing it through this tank. Water at the top, brine at the bottom, and in between a layer of intermediate density. With this experience of the behavior of light, we can look at the simplest device for producing optical pictures, the pinhole camera. The front is an easily changed piece of opaque paper. The back, a greaseproof paper screen. As an object, we shall use this carbon filament lamp. A pinhole in front. Stand back about a foot from the lamp, and we see a dimly lit picture of the lamp on the screen. Several pinholes. Several pictures. More pinholes. More pictures. If I slide this lens across the front, all the pictures come together into a single image. The lens is bending the rays so that they all pass to the same place, where the image is. Now let's actually see the rays bending. For this we need a smoke box with a lens inside. This screen allows only a few rays from the lamp to pass into the box. This device produces the smoke. Puff the smoke into the box, and the rays will become visible. The lens is bending the light falling on it, and the light is gathered together. So the image is formed. But of course, the light passes on through the image, and from here, I can again see it on the paper. If I withdraw the paper, I can still see the image at the place where the paper was. The image is between me and the lens. Here. If I hold the lens close to my eye and look at my thumb through it, I see an enlarged image of my thumb. Of course, if I withdraw the lens, my thumb looks blurred. Its image must have been much further away, beyond the lens and beyond my thumb. A virtual image. I'm using the lens as a magnifying glass. We've got another lamp on the other side of the laboratory. I can use this weak lens to throw an image of the lamp onto a piece of paper. And look at the image with a magnifying glass. remove the paper, and obviously I've got a simple telescope. The behavior of lenses and mirrors can be made very clear using streaks of light, or ray streaks. This simple apparatus has been designed for pupils' individual use. It consists simply of a car headlamp bulb, which will be my object, and a metal comb. Let's put this cylindrical lens in the path of the rays. The rays are bent to pass through an image here. A second lens bends the rays even more. A thick lens bends the rays more than a thin lens. The spherical aberration is quite noticeable, but the planar cylindrical shape has been deliberately chosen so that we can see the way this aberration depends upon the shape of the lens. Let's turn it round. This is a negative lens. We'll cut off the unwanted light with these barriers. The rays are diverging and appear to come from some point back here. Looking through the lens, I can see the point where the rays appear to come from. Pupils can be encouraged to look through lenses in this way. Let's go back to our first lens. And put in the barriers now to cut out this unwanted light. As we move the object away from the lens, the image moves closer. As we move the object towards the lens, the image moves further away. Now the rays are not converging at all. They appear to come from some point back here, behind the object. The lens is forming a virtual image. If I were to look through the lens again, I should be able to see where these rays appear to come from. The behavior of a lens can be made clearer if we use a single ray. The ray can be made sharper by putting this supplementary lens behind the slit. There. Now we slide the lens across the ray and watch the way it's bent. There, the ray isn't being bent at all. Even if I twist the lens like that, the path of the ray is still in the same direction as it was before it hit the lens. This undeviated ray is very important in optical drawings. Another way to make the behavior of a lens clearer is to return to our comb, place the lens in front of it, and then to slide this slit, which only lets a few rays through at a time, across the face of the lens. There we can see how all the rays pass through the image point. We can look at the behavior of mirrors in a fan of rays. Here's a plane mirror. And here's a curved mirror. Look at the caustic curve. If we slide this slit across the plane mirror, we can see how the image, which is being formed by just 3 rays, moves around the caustic curve. A beautiful demonstration. Now I'm going to use 2 lamps. Obviously it's best to put some barriers in. With two lamps, we can see how an extended object forms an extended image. This lamp represents the bottom of the object, this lamp the top of the object. If I move these lamps back, I can make a model telescope. Here's my eyepiece. The eye ring is clearly visible. We can mask the effects of spherical aberration by using a three-slit comb. In a real telescope, spherical aberration is reduced and the field of view is increased by putting an extra lens in here, called the field lens. Many similar experiments will suggest themselves with this apparatus. A model microscope, refraction experiments, prisms, and so on. The eye itself is an optical instrument, and we ought to consider its structure and working. Here is a good model of the eye. The 5-litre flask has been filled with water, which has been coloured by the addition of a little fluorescein. The three lenses on the front represent long sight, short sight, and normal sight. This screen will cut off unwanted light and act as a holder for supplementary lenses. For a normal eye, an image of the source is formed on the back of the flask. For a short-sighted eye, an image of the source is formed in front of the back of the flask. I can correct this with a supplementary diverging lens. For a long-sighted eye, an image of the source is formed beyond the back of the flask, and I may correct this with a supplementary converging lens. In this film, as in the Nuffield Physics course, optical instruments have been placed first. It is, after all, an understanding of these that will be important to those pupils who will carry only a general memory of optics into later life.